0, -1. All right, hi, welcome back. Math 234. I'm still your host, Steve Dragu. Today we've got chapter 15, section 2, as we're finally into chapter 15. So we're looking at more integrals today. That's the game plan. So let's bring that up. So the first section we did was double integrals. And now the second section is iterated integrals. And at first glance, it seems like those two things might be the exact same thing, which they almost kind of are. To take it back to the way that we talked about this sort of thing in Calc 1, we had integrals and antiderivatives, but then integral just went out and we pretty much stopped calling them antiderivatives, even though that does mean something very technically slightly different. Double integrals and iterated integrals are basically the same thing, where there's a very slight technical and semantic difference, and one that I don't plan on ever really talking about much, except for right now, because we're introducing them. So the double integral is the nomenclature, the preferred nomenclature, that we'll use pretty much every time we want to talk about one of these kinds of things. But if you're looking for the specific difference between a double integral and an iterated integral, or iterated integrals, the iterated integrals is just a series of two integrals in succession. An easy way to check whether you have a double or an iterated integral is by looking at the differential. The double integral has the differential dA, which talks about a small change in the area of whatever region we're integrating over. Whereas iterated integrals have something like dx dy, because there are going to be two integrals, one for x and one for y. Again, I don't really plan on making that a big deal at any point in time. It's not like you're going to be quizzed on the difference between the two words or the two ideas. It's just, if you got curious as to why we have different words to talk about what appears to be the same thing, that's why. Double integrals, again, is going to be the thing that wins out. We're just going to call these things double integrals pretty much all the time. Again, slight semantic difference between them. But anyway, getting into what these things actually are, they're how we're going to evaluate double integrals. In the first section, we really just looked at evaluating them geometrically, where we said that the double integral of some function should just be the volume that's underneath that surface, just like how a single integral was the area under a curve. Now, double integral, volume under a surface. But practically speaking, anytime we want to really calculate a double integral, we'll just break it down into a series of two integrals, one for each of the two parameters that we're integrating over. The most basic and obvious of which are x and y. We'll be integrating over some region that's usually in the xy plane. That's like our standard approach to double integrals. And at least for today, we're just going to be looking at integrating over rectangles. The reason we're picking rectangles is because that means that both x and y can be bounded by constant values. So if we just look at integrating over x on some interval between a and b, y also on some interval, so I just used a and b, we'll now go to c and d to represent the y integral. Yeah, that's fine. So yeah, again, just over rectangles because we're in the rectangular coordinate system. And I'm also bringing that up because we're going to break out of that rectangular coordinate system fairly quickly. But not today. Again, today we'll just focus on rectangles. So maybe a quick graphical or quick visual look at what these integrals are doing when we're taking, what is that? Looks like a dx integral in figure 1, it's dy integral in figure 2, where we're effectively going to be kind of passing that shape, that pink shape that's there in the middle of the solid, through that shape and kind of adding up all of the areas that we get to ultimately end up at some kind of a volume. Because again, I want to keep in mind that these double integrals should result in a kind of volume. Or at least that's our best geometric interpretation. of a double integral. So with that said, let's go do an example. Starting with a pretty straightforward one. I want the iterated integral, the one that's on screen. We're going to do, looks like in order dy first and then dx, which means I do want to come and talk about one other thing, which is the order of integration. We read from the inside out when we're doing these double integrals. So the inside integral, or one of the two S curves that I have there at the beginning, matches with the inside differential. So you can see I've got them color coded up there, but then forgot to actually specifically say something about it. So the dx integral is going to be first because it's the one that's most inside, and the dy integral is on the outside. Imagine adding in parentheses in between our dx and our dy, and we can like nest those things to work inside out, which is sort of the rationale behind why we do it that way. So similarly, if I switched the order and did y first instead of x, I would need to move the y bounds to the inner integral. So in this one here, we are doing dy first because it's the innermost differential. Order does matter, though we will talk about how to change the order. So if we're gonna work through this thing, let's see what we got. Well, I'm gonna leave the x integral alone for now, and I'm just gonna evaluate the y part. So this will be x squared times, just like partial differentials or partial derivatives. There we go. When I'm doing a dy integral, or when I'm doing an integral with my variable as y, I'll be treating x as though it's a constant. Hi there. Oh, the integral on the inside is the one for dy. So I'm not really doing the 0 to 3. I've written that down because I'm leaving it alone. I'm not touching that part yet. Whereas I am going to do the y integral, which would give me y squared over 2. And I am evaluating that from 1 to 2 dx. All right, so again, it's the 0 to 3 part that got left alone, and it's the inside integral that's being evaluated. So you can see now I've shifted my bounds from the integral sign over to the evaluation bar at the edge. I actually don't know what we call that thing. It's not that important, I don't think. But anyway, I can then plug those numbers in. I'm just doing a standard integral of y dy from 1 to 2. I think I'm going to get 4 over 2 minus 1 over 2, which will be 3/2. And now that that's a constant, I'm just going to factor it to the outside of the integral. 0 to 3 x squared dx. Okay. So now that I've done the first integral, did the y integral, I can evaluate the second one. Iterated integrals. Two integrals in quick succession. In order. So this should now be 3/2 halves, times that x integral, which I believe is x cubed over 3. Come back here. X cubed over 3. This one will evaluate from 0 to 3. Which looks like 3/2 times, if I plug some of this stuff in, what are we going to get? That looks like 27 over 3 minus 0 over 3. which am I out of space? No, I've got a little bit more space. I can write one more line down. That looks like 27/2 in the end. So if I back out and just look at the whole thing again, those are all the steps. So again, I'll just look at doing two integrals in order. I do the one on the inside first. And again, when I am doing that integral, just like with partial derivatives, I treat the other variables as if they were constants. I don't think it made too big of a difference. So
Why?
say it one more time. Aha! So the question was, after I do the inside integral, do I just treat it as a constant? By the time I do the inside integral, it then is a constant, right? Because I've evaluated between two numbers. So all of the y part is just a number now. So there, by the time I get to my second integral, I should only have one variable or one parameter left. Yeah, which I can see happened right here. After I did all of the yellow part, there's only x remaining. And that'll be pretty consistent. Pretty consistent. That'll always be the way that it needs to be. By the time I get to my second of two integrals, I can only have one variable left. If I still have two variables, something's gone wrong, and you should double check your work. Yeah. Right, there's a remark on here that we want to talk about. We will occasionally look at some of the more difficult integrals to do. So for the most part, the complexity in these problems, because iterated integrals themselves, at least when we're going over rectangles, is pretty straightforward. Not a ton of added difficulty from the new Calc 3 perspective, if we're just looking at rectangles. So to compensate for that in the homework, we asked some harder integral questions on this set. So you might need to remember things like or the derivative of like arc tangent or arc sine. I think those come up. We'll need a couple of integration by parts examples. But for the most part, in fact, for the all part, we'll be containing any difficult single integrals to the homework and not so much on the quizzes or the exams because we need more time to talk about the actual more fun topics. So expect to see relatively straightforward integrals on quizzes and exams with the more complicated single integrals showing up on the homework. I hope. Let me know if it's different from that, because that means we should make some changes. But if we take a look at this one, looks like we're going to do the double integral of root y over x squared dA, and R is the rectangle bounded by x equals 1, x equals 3, y equals 0, and y equals 1. So notice this time we're just given dA, and basically told, I don't know, you figure out what the order should be. Meaning we can choose which integral to do first, whether we want to do dx or dy first. A lot of the really fun questions, fun being, you know, a sort of a relative word there. A lot of the fun in some of these double integral problems comes from choosing the order in which to integrate x and y in. Because oftentimes we'll find that something is nicely integrable if we go in a specific order, but might not be so integratable if we go in the other order. But we'll mostly save some of that complexity for later. For now, we could solve this one in either order. Either way would work. Since we did dy first last time, I'm just going to do an example of doing dx first. Because honestly, I think in this one, it really doesn't matter what order we go in. Though maybe the y integral would be slightly easier. Again, don't think it's going to matter super over much. So let's do x first, which means I'm going to do from 1 to 3. This is square root y, square root y over x squared dx, and then dy. In fact, let me just kind of pop over here. I'm going to gray this out for now. Same with its bounds. I'm going between 0 and 1. Then gray this out, going between 0 and 1. Highlight the fact that I just want to focus on the x integral first. Why don't we just pop you into gray as well? Okay, so x first. Meaning, what are we going to get? After integrating this thing, 0 to 1, and the square root of y. We also won't really do much with that yet. X, however, that's the thing we wanted to integrate. If I am integrating 1 over x squared, because that's effectively what I'm looking at. I guess I'm ignoring the root y. I'm pretending it's just a constant for right now. I want to integrate 1 over x squared, which is really x to the negative 2. That's the way that I would think about that. Because that means I can just apply my power rule to say that this is negative, let's see, 3 to the negative 1 minus a negative 1 to the negative 1. And then dy still hanging out right there. Slide that maybe slightly up because I think I'll need more space. So this thing is, what do I get if I evaluate negative 1/3 plus 1 over 1? I think that's 2/3. Negative third, negative 1/3 plus 1 is 2/3. And then I still have the y integral to go. From 0 to 1, this is the square root of y, hey, square root of y dy. And then that thing can also be integrated 2/3 times. Let's see, if I integrate the square root of y, remember that y is really, or square root of something is really just something to the 1/2. So that'll be y to the 3/2 times 2/3, right? Y to the 3/2 divided by 3/2. So 2/3, looks a little bit too messy if I do everything in yellow. So this will be 2/3 times 1 to the 3/2 minus 2/3 times 0 to the 3/2. Which in its final form, 2/3 times 2/3, which is 4/9. Zoom back out and look at this problem again. Entirety. Yeah, what's up? Yeah, for sure. The antiderivative of x squared, if I just write some notes over here in the margin. This is the integral of 1 over x squared dx is really the integral of x to the negative 2 dx, which is negative x to the negative 1, or negative 1 over x. Those are my thoughts there. I'm supposed to fill in that same work for the y integral that I did. This is the integral of the square root y dy, which is y to the 1/2 dy or y to the 3 halves divided by 3 halves. Which I then rewrote to be 2/3 y to the 3 halves. Since I can divide by fractions. Do, 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 do. So, assuming that part went well, I might have noticed here in the end, particularly if I'm looking down in the bottom row, mark that in purple, since that's where that 2/3 came from. Effectively, all I did here was I integrated x, completely ignored y, got 2/3, integrated y. There was no x to ignore anymore, but if I had done it first, I could have ignored x. And I got 2/3, again, without even looking at the other variable at all, multiplied them together and got 4/9. In particular, if we look at just completely separating those two integrals, doing the integral of 1 over x squared dx, doing the integral of root y dy, I get 2/3 for both, multiply them together and get 4/9. That's the same answer I got when doing this as an iterated set of integrals, where I had one inside of the other. Similarly, I want to talk about the first problem again. If I just did the integral of x squared from 0 to 3 and the integral of y from 1 to 2, I get 9 times 2 minus a half, right, as my two independent integrals. Right, I'll look back up here at this guy. Again, just integrated y, completely ignoring x, and integrated x, wishing I could completely ignore y. I find that the result of these iterated integrals just ends up being the product of two single integrals. Going back to our Calc 1 ideas. And that is a unique property of separable functions. So bringing up another theorem from out of the textbook, if our function is separable, meaning I can write my function as a bunch of x's, or a function that depends only on x, multiplied by a function that depends only on y, then I can evaluate the two integrals separately and just multiply them together. Here, when I'm saying separable, I mean separable by multiplication. Maybe a stand-in word there could be factorable. If I have a factorable function, I can use this idea where I can just separate out my two integrals into two unique individual pieces. And I don't mean separable by addition, right? X plus y is not going to be a separable function. So I can't do just an x integral and then just a y integral and multiply them together. My function for x plus y, but x times y is separable. Again, the idea here being that my function can be written as something that depends only on x, multiplied by something that depends only on y. And we had that in both of the two cases above. This function, root y over x squared, if I just rewrite what that thing is, f of xy, which is root y times x squared. This is really x to the -2 times y to the 1/2. If I also just change things over to powers. But I can see that the thing is separable. That function is separable because I can pull all of my x's out in front multiplied by all of my y's in the second half. Same thing with the question above, probably even easier. X squared times y is x squared times y. Another separable function. So real nice when we have that, because we can just evaluate our two integrals independently, but we don't get to hold on to that fun idea forever, sadly. And in fact, in the very next equation, we don't do that anymore. Now the next couple of integrals, or at least two of the next three, end up being pretty involved. So I've got all the work done out already, and I just want to hit some of the highlights as we go through that work. 'Cause again, these can get a bit long and messy depending on how rough the integral itself is. And rather than getting too lost in all of the details, I want to focus on some big picture stuff and then say when we're really trying to learn this iterated integral stuff, doing the homework later on, come back and look at the notes as you're trying to piece your way through it all. But I'll highlight some of, I think, of the key steps as we go through here and to try to take this more complex looking work and simplify it into a couple of simple, big ideas. First, I want to look at my function, which is x times sine of x plus y, which, as it turns out, is not a separable function. I can't really factor out my x's from my y's because I'm adding them together on the inside of a sine function. You maybe could say this function is separable because it's not like the least separable function I've ever seen. We could use a sine sum formula, which I believe is sine x sine y, or sine x cosine y plus cosine x sine y. I used to be a trig instructor. I still remember the angle sum formulas. So I could break that thing apart, and then I'd have a sum of two separable functions, and I could evaluate two double integrals that way if I wanted to go through that work, which I don't think is what we did here. In fact, I know it's not what we did here because I've looked at this one already. But we're going to treat this thing as non-separable, meaning I've got to integrate this thing in order. So let's go talk about the bounds. I look over here and I see this guy right there. I want to rewrite my bounds for x in a way that maybe makes more sense. When I'm looking at this thing, I see that I am within pi over 2 of some center value for x, and that center is also pi over 2. Right, looking on the inside, this pi over 2 right there tells me that the center of my x interval is pi over 2. And on the outside, that's telling me I'm within pi over 2 of that center. So if I look pi over 2 to the left, I'm at 0. And if I look pi over 2 to the right, I'm at pi. It's pi over 2 plus or minus pi over 2. Same thing with the y interval, except now not every number is pi over 2, so it might be easier to talk about this one. This time my center is at pi. So y's center value is at pi. That's right in the middle of its interval. And I'm again within pi over 2 of that center. I'm within pi over 2 of pi. So if I look to the left, that's pi over 2. And if I look to the right, I'm at 3 pi over 2. Or maybe I'm looking down and looking up since this is the y value. Y typically runs up and down in 2 space with x running left and right. But I digress. Cool. So my x bounds between 0 and pi, my y bounds between pi over 2 and 3 pi over 2. So I see those show up here and here for x and pi over 2 and 3 pi over 2 for y. So that was my first step, just figuring out the bounds that I want. Also, I mentioned earlier, but I don't think I showed it, that when we're looking at these iterated integrals, we could imagine putting some large sets of parentheses in there to talk about how the integrals are nested inside of each other. So we want to work from the inside out. Here's an example where we do have those parentheses added in. Right, so my iterated integral is really one integral on the inside of parentheses surrounded by another one. which is why we start on the inside and work our way out, just like with regular functions. But cool, so we have an entirely y integral first. Here's my dy part, here's my dx part. Purple's not showing up as well against blue ink, but oh well. And when I actually go to do this y integral, right here in this step, I really just am imagining integrating the sine of y dy to get negative cosine y. Right, I have some extra stuff going on, right? I really have x times sine of x plus y. But since I'm only really focusing on the y parts, I'm not thinking very hard about x as I'm going through the y integral. So I'm really just pretending like that thing is sine y dy. I know its integral is negative cosine y. So I expect my answer to look like negative cosine of roughly y. I know I need to go back and worry about all the other pieces that are in there. For example, my input angle isn't just y, it's really x plus y. I also have that x that was multiplied out in front, but when I'm actually doing the integral part, when I'm actually evaluating an integral, I'm thinking mostly about the integral of sine and it being negative cosine, rather than getting too lost in the smaller details. Because then I do still need to like plug that in and evaluate between a couple of bounds, and also I end up with something that isn't super nice to try to integrate either. I have this cosine of x plus 3 pi over 2 and cosine of x plus pi over 2. And I am going to rewrite that stuff using some more trig identities. In particular, the trig identities at play here are the cofunction identities. Cofunction identities. If you want to look that stuff up later, it might be helpful. But in brief, all 6 of the trig functions get paired to a cofunction, and it's pretty easy to remember which one is which, because the function and cofunction usually go something like sine and cosine, right? Sine and cosine. So the cofunction of sine is cosine. Similarly, the cofunction of tangent is cotangent. Cofunction of secant is cosecant. So you just add a co in there. Also, you've got the cofunction of cosine is cosine. But cos are like negatives. Cosine is just sine. And we don't ever really say cosine because that's just weird. Anyway, back to what we're actually trying to talk about. Converting those rather ugly looking cosine functions into a more simple sine function. Again, using cofunction identities, the reason that these things work is because sine and cosine and all of our trig identities are all based on opposite and adjacent sides inside of some right triangle. And as it turns out, if I look at both of the angles that are in that right triangle, they are complementary angles. They are complements of each other, meaning that they both add to 90 degrees if I put them together. So these cofunction ideas are very tied to the ideas of complementary angles. In particular, pi over 2 being rather important because that's 90 degrees. That's where those identities are coming from. But again, it's just there if you want to look it up later. I think it's probably worth actually going back to look at cofunction identities because it will help out with some other integrals later on, particularly when we're doing a lot of integration with sine and cosine, which we end up doing a ton of because we're going to look at polar coordinates and their extensions into 3 space. But again, I keep getting ahead of myself. So again, might be worth looking up the cofunction identities. And also Pythagorean identities. I'll just add that into Pythagorean identities. You probably know that one already, though. That's sine squared plus cosine squared is equal to 1. That's one of our Pythagorean identities. There are two more that might be worth it. But I digress. We need to go do some other things. First, we're simplifying our integral down to just x times sine x. That's why we brought in the cofunction identities, because it gave us a slightly nicer integral to look at. But then it's just integration by parts to ultimately solve this thing the rest of the way out. One other level of detail I want to add in right here before I look at something completely different, which is what's over there to the right. I'm getting there, I promise. Is a handy notation for integrating cosine from 0 to pi. In particular, that's just 0. And rather than looking at the actual integral and plugging numbers in, I think this integral is rather nice to identify, or it's rather nice to solve geometrically. Because if I am looking at 0 to pi, I am looking at quadrants 1 and 2. If I remember the way that my unit circle works, it goes from 0 all the way around to 2 pi to get a complete circle through. So from 0 over to pi just covers the first two quadrants, the two on top. And in those two quadrants, cosine is positive in the first one and negative in the second one. Sine and cosine are also very symmetric functions because they just go through a circle. So the area underneath cosine in the first quadrant is the same as the area underneath cosine in the second quadrant, same as the area underneath cosine in the third quadrant, and da-da-da-da-da-da. The difference, of course, between those being that sometimes it's positive and sometimes it's negative. For cosine in particular, it's positive in the first and negative in the second. So those two areas add to 0. Another handy integral, or another set of handy integrals, would be evaluating either trig function, either sine or cosine. Let's call it sine theta d theta. From 0 to 2 pi always results in 0. 0 to 2 pi of cosine x dx. Also 0. If I integrate a trig function over its full cycle or all the way across its period, I'm going to get 0. By that same argument I used a moment ago. The area in each of the four quadrants, or the area under the curve in each of the four individual quadrants, should always be the same. In fact, we'll see in a minute kind of what that'll look like. I'm getting a little, or it's just, again, getting ahead of myself. Leave that for later. Since each of those four quadrants all have equal area and half of them are positive and half of them are negative, I'll always get 0 if I integrate over a full period for either sine or cosine. But since I'm on the topic of evaluating some trig integrals and doing it geometrically, another one that I think is very handy to know because of how frequently it comes up is the integral of sine squared or cosine squared from 0 to 2 pi. Because we'll see this one show up a lot. And its actual integration, if you're doing it the algebraic way, gets a little bit annoying because you've got to remember the double angle formula, make a substitution, then integrate two separate parts, and then evaluate at 0 and 2 pi. Kind of annoying to do it that way, but geometrically it has a very nice solution. And one that I think is very, very, uh, what's the opposite of time consuming? Efficient. Yeah. Yeah, I like efficient. Yeah. So the argument that I want to make here. I know sine squared plus cosine squared is equal to 1. And that is true at any single input angle. So if I just graph those two things, is what you're looking at here. Uh, in particular, I've graphed sine squared. It's the function in blue, which means that the function highlighted in magenta right above it is 1 minus cosine squared. But really, we're going to use that as a stand-in for cosine squared. It has that same shape, just it's been reflected and shifted up by 1. But the nice thing about that is that if I add these two things together, I get just a rectangle. And in particular, I'm looking at this rectangle over one full period or one full cycle around the circle, which means I'm looking from 0 out to 2 pi. You can see those two things added together make a rectangle with a height of 1, because that's the height of a sine or cosine function, or the amplitude of a sine or a cosine function, and a base of 2 pi. Meaning that whole rectangle has an area of just 2 pi times 1, or 2 pi. Now, again, using the fact that I know sine squared and cosine squared are symmetric, because they go through the same cycles, just going around a circle, I should expect that the area of these rectangles is half from the sine squared function and half from the cosine squared function. As long as I look at going over a full period, that'll hold up to be true. Meaning, if I want the integral of sine squared over 2 pi, from 0 to 2 pi, it's full circle, sine squared, that area, should be just half of the rectangle. Meaning, the integral of sine squared from 0 to 2 pi is just pi, half of this rectangle. And cosine squared would be the other half, since sine squared plus cosine squared added together must be 1. So again, a convenient integral, one that will save you a lot of time, one that I would recommend kind of familiarizing yourself with the geometric interpretation for is this guy right here. Sine squared from 0 to 2 pi is equal to cosine squared from 0 to 2 pi. Each are half of that rectangle, so they each have a measure of pi when I integrate them. These integrals can be subdivided a little bit. So I can see just by looking at the graph that's there, from 0 to pi, I just repeat that cycle a second time to get 0 to 2 pi. Since these things are squared, they're no longer dipping below the x-axis. This thing is actually symmetric only through a half circle instead of needing a full circle. So I can divide the thing in half, and this idea still holds up. That the integral from 0 to pi is pi over 2 for both of them, because again, they're both half of that rectangle. And the final way I can subdivide these is into quadrants. Because sine and cosine are also going to be very symmetric within a quadrant. It's just that one measures from the x-axis up, whereas the other would have the same cycle from the y-axis down. But that's as far down as I can subdivide them. Integrating sine squared over just a single quadrant will get me pi over 4. Same thing with integrating cosine squared over a single quadrant. I'll get pi over 4. If I try to break it down further than that, the geometric explanation is not nearly as nice. So we'll just go back to evaluating it the algebraic way. As long as we stick to integrating over full quadrants, or most of the time, a full period, this substitution is nice. Hopefully I've made my case there. So I think we've got one or two more to work through together, and then we'll call it a day. So another example, finding the volume of a solid enclosed by the surface Z is that between the planes Z equals 0, X equals 0, X equals 2, Y equals 0, and Y equals pi over 4. So all told, what do I want to do here? I want to evaluate some double integral over a region R, where the function I want to integrate is x times secant squared y dA. And I want to start trying to solve this thing. And it seems like forever ago that I brought this up now, since I got distracted by trigonometry. But my integrand this time, x times secant squared y, that thing is separable. So I could write this as an x integral multiplied by a y integral. So integral of x dx times the integral of secant squared y dy. And then add in my bounds. So x is from 0 to 2. And y is from 0 to pi over 4. And then the fact that we're also bounded by z equals 0 just means we're looking for the volume above the xy plane, since z equals 0 is the xy plane. So this is still the standard interpretation of volume that we've been using for double integrals. That part's not changing. But then I can evaluate these two things independently and go from there. So on the x side of things, this looks like 4 over 2 minus 0 over 2. And on the y side of things, the integral of secant squared is tangent. So helpful to remember that. This looks like the tangent of pi over 4 minus the tangent of 0, which is going to be 2 times 1, which is just 2. So a couple helpful things to remember there from the unit circle. The tangent of pi over 4 is 1. Sine and cosine are equal to each other at pi over 4. Anything divided by itself is 1. Except maybe for 0, but we'll get back to that. Oh, will we? Doesn't matter. Tangent of pi over 4 is 1. That was the point I was trying to make. And then tangent of 0 is 0. Right. And then for the last one on our set, an average value of e to the y times the square root of x plus e to the y should be or 1 over the area times the double integral over the region. Yeah, whatever. Over the region. And our integrand is e to the y times the square root of x plus e to the y dA. We're integrating over some rectangular region given by the 4 vertices there. Those things make a rectangle. And we finally get a fun decision of which integral it would be nicer to do first. And actually, it probably still works out relatively easy either way. It ends up being not too bad, no matter which way we swing it. But one thing that's worth noticing is that I've got an e to the y plus something on the inside of a square root, and also an e to the y on the outside of that square root. So I'm thinking there's a pretty nice looking u substitution. Since the derivative of the inside is just e to the y, or rather the y partial of the inside is just e to the y. So I see a sort of u substitution coming together nicely there. Meaning when I go to do the y integral, I'll have that part first. I'll have that U substitution to do. Now, I know that I am out of time because it's 10 after already. So I will say if you got to be somewhere, feel free to leave right now. But I'll also just take 2 minutes and solve the rest of this integral. So if you want to stay for that, that's what I'm going to do right here. So my area. Calm down, buddy. My area, I've got an x length of 4, I've got a y length of 1, so the area is 4 times 1, and I need the double integral of, I'll do x second, so 0 to 4 here, and 0 to 1 for y. I have, there we go, e to the y root x plus e to the y dy first, and then dx. So this will be 1 over 4 times the integral from 0 to 4 of whatever I get when I evaluate y at 0 and at 1. This is going to be, if I slide you out, I'm integrating the square root, so I'm going to get a 2/3 on the outside. I'll have an x plus e to the 1 to the 3/2 minus x plus e to the 0 to the 3/2 dx. And then I need to integrate this thing from 0 to 4 dx. And it looks like both of those things get integrated to the 5/2 power, which means I'll need to multiply by 2/5 and start plugging some things in. This will be 4 plus e to the 5/2 minus 4 plus 1 to the 5/2 minus 1 plus e to the 5/2 minus a negative. Wait, that's not supposed to be a 1. That's supposed to be a 0. There it is. 0 plus 1 to the 5/2. That might have been the first small math mistake I made today. Small number mistake I made today. It's not bad. We're advancing. And as you can see, this integral is kind of ugly looking by the time I evaluated it all. I would leave my answer exactly like that. I would not try to simplify it further. So if this were a Weber problem, I don't know, just type that in. Anyway, that's it for today. I will see you guys again on Friday. We're doing even more double integrals. Okay, bye, 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 bye. Bye, bye. Okay, actually, there's one more example of just some work to go through, but again, it's a super mod looking guide. So here's some more work for you to look at. Okay. But for reals. Okay, bye, 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 bye.